So far we've just dealt with slope-intercept form, which again is y equals mx plus b. But that's really only convenient when we either know the slope and the y-intercept or want to know those two. So if I don't know the y-intercept, we have other forms that are useful. So for example, what we're going to learn today is what we call point-slope form. And guess when we would use this? Well, yeah, when you know a point and you know the slope. So it's an equation of a line when one point is known and the slope is given. So we're going to use m for the slope, just like always. And then we're going to use x1, y1 for the point that is known, the points that's given. So here's our slope-intercept, or our point-slope form, I'm sorry. It is y minus y1 equals m times x minus x1. And this actually came from something. I'll explain. So if you remember your slope formula, m equals y2 y minus y1 over x2 minus x1. If I wanted to get rid of basically this denominator of the fraction, I wanted to get rid of the fraction, I could multiply by the fraction. I could multiply by x2 minus x1, and these would cancel each other as long as I do it to the other side. If I multiply by x2 minus x1 on that other side. And then if I rewrote this and flip-flop the spots, I'd have y2 minus y1 equals m times x2 minus x1. Well, isn't that this right here, except instead of y2, we just wrote y, and instead of x2, we just wrote x? They're the exact same thing. So that's where that got derived from. We just use our slope formula. And the other thing is, we usually like y by itself. So for example, up here in our slope-intercept form, we have the y by itself, y equals. I could do the same thing here. If I wanted to get the y by itself, all I'd have to do is just add this y1 over to the other side. And it would look something like this. Y equals m, the slope, times x minus x1. And the m always goes with the x's anyway, and then plus y1. So this is what we really want to use right here. That'll be super helpful. Okay, I should know it whether it's on the other side or not, but that's the case. So y equals m times x minus x1 plus y1. So you never plug anything in for the y or the x. You only plug in for the x1 and the y1 and the m. So for example, if I look at this left one over here, it has a slope of 2 and a x1 of 3 and a y1 of negative 2. So when I'm given a slope and a point, I can use my point slope. So I'd say y equals, okay, well here's the slope, so 2 times, and then x minus, well, x1, which is 3. And then I'm going to say plus y1, which is negative 2. Well, instead of putting plus negative 2, I could really just write what? Negative 2 or minus 2. So that would be that right there. And then the same thing with this one over here. I'd say y equals slope 1/3 times x minus x1, so negative 4. Well, minus a negative is really adding a positive, and then plus 7. Done. What if I wanted to take point slope form and turn it into slope-intercept form? Could I do that as well? Sure. It'd be nice and easy. If I look at this left one, if I wanted to write this in slope-intercept form, I could just distribute my 2, and I'd have 2x minus 6 minus 2, right? I got to bring down my minus 2. And then combine like terms, so I'd have 2x, and minus 6 minus 2 is really minus 8. So these are the same thing. Right, I could just turn point-slope form into slope-intercept pretty easily. So let's just look at a couple equations in point-slope form and write what the point and the slope is. So in this case, I have y equals 4 plus 8 times x plus 2. I'll write my point-slope form over here in a sec, but what would the slope be? What would my m equal? Yeah, it's the number that's in front of what's being multiplied to the x term. So 8 should be my slope. And then what would the x1, y1 point be? Well, x1, is it 2? No, just think about it. It's x minus x1. So x minus negative 2 is really plus 2. So this is a negative 2. It's always the opposite with the x's, okay? That's kind of the tricky one. And then for the y one, well, that's just positive 4 right there. If it was on the other side, let's say I said y minus 4, then it would be a positive 4 because it's kind of the opposite, right? It's y minus, kind of like it is x minus. And that's just write the 2 forms. So it could either be y minus y1 equals m times x minus x1, or the one we like to use is y equals m times x minus x1 plus y1, right? We just add the y1 over. How about this one? Let's do it a little bit quicker now. What would the slope be? Right here, negative 2/3. Always use the sign that's in front. Don't forget about that. What would my point be? Well, 2, not negative 2, but 2, right? Because it's x minus x1. And then 5. 2, 5. There we go. So point slope form kind of comes in handy when, you want to use points and slopes. All right, so let's use this for a situation now. It says Silo and Jenny conducted an experiment in which Jenny walked at a constant rate. Find the slope of the line that represents this situation. Well, we have to decide which one of my x's and y's. Well, x is for time, y is for distance, right? Because the time is usually always on the x-axis. We'll talk about independent and dependent in just a little while. So how do I find slope? Well, that's, remember, our y2 minus y1 over x2 minus x1, or if you just always remember, subtract your y's on top. So in this case, we'll take 4.6 minus 2.8 and subtract your x's on bottom. Well, since I started with 4.6, I have to start with 3 and say 3 minus 6. And that would give us 1.8 over negative 3. And let's clean that guy up. So 1.8 divided by negative 3 is really negative 0.6. Or remember, we like to write it as a fraction. So I'm going to go into math, change to a fraction, negative 3/5. That's much cleaner, much cleaner. So negative 3/5 for the slope. Okay, let's get used to doing that, changing that to a nice fraction. All right, let's write it a linear equation in point-slope form using a point and the slope you found in problem 1. All right, so we're going to go with our y equals, remember our slope, which we just found is negative 3/5. And then we have x minus x1 plus y1. Well, what can I plug in there? Do I know any points that would be on this line? Sure, I have 2 of them. Look up at my table. Here's one of the points, 3, 4.6, and here's one of the points, 6, 2.8. Does it matter which one you plug in? Not at all. So which one do you want to do? Let's grab the first one. So I'd plug in 3 for my x1 and 4.6 for my y1. And there we go. I'm done. I got it in point slope form. Could I have wrote the other one? Sure. If I would have done that, it'd just be y equals negative 3/5 x, and then what? Minus 6 and plus 2.8 instead. Either one works just fine. And if I wanted to get it in slope-intercept form, I could just distribute and then combine like terms in the end, but we don't need to do that. All right, so let's write the equation in point-slope form through the points negative 3, negative 4, and 7, 9. Well, if I want to write it in point-slope form, what do I need to know? I need to know a point, which I do. I know 2 of them, so I can pick either one. And I need to know the slope. So first of all, let's go ahead and find the slope. We'll subtract your y's on top. So 9 minus negative 4 over, and then since I did 9 first, I got to do 7 first. So 7 minus negative 3. And that ends up being 13 over 10. So 13/10. And I could also count that as well. I could have counted the rise and the run. So up 13 and right 10. Same thing works. And then to do it in point slope form, I say y equals 13 over 10. There's my slope. And x minus x1. Well, it just depends which one you want to do. Let's say I do this first one. It'd be x minus negative 3, which is really x plus 3 minus 4. That'd be one way to write it. Or I could say 13/10. It doesn't matter which one you do. If I pick the second one, now it's x minus 7 plus 9, right? X minus x1 plus y1. So either one of those would be just fine. All right, so point slope form is very useful when you know a point and a slope.